My name is Lauren Allen, and this is my Pre-Calc 1113 Fall Video Homework 2. So, before we get started, I want to look at a table of contents. We're going to be reviewing 2.4 in our transformations. We're going to go over cosine and sine functions and how to deal with the transformations. We're going to go through tangent functions and their transformations, special right triangles, and how to use the side lengths using the rules of special right triangles, and then trigonometric identities and quadrants, and finding the values of various trigonometric functions using the proper identities. So, first thing we're going to do is review. We have vertical shifts, horizontal shifts, and reflections. Vertical shifts are never going to happen directly to x, so it's going to be outside. So if it's plus c, we're going to move the graph upward. And if it's minus c, we're going to move the graph down. Horizontal shifts are always going to happen directly to x, so if it's plus c, it's going to shift to the left, and if it's minus c, it's going to shift to the right. And then for reflections, if we have a negative f of x, it's going to be a reflection across the x-axis because all of our y values are going to become negative, and if it's a negative x, then it's going to be a reflection across the y-axis because all of our x values are going to become negative. And if it's both, then it's a reflection across the x and the y, or the same thing as a 180-degree rotation. So with our second review, we have vertical stretching and shrinking, horizontal stretching and shrinking, and inverse functions. So with vertical stretching and shrinking, it's going to be outside of the x, and if c is larger than 1, it's going to be stretched by a factor of c, and if c is between 1 and 0, it's going to be shrunk by a factor of c. For horizontal stretching and shrinking, done directly to x, and then if c is greater than 1, it's going to be shrunk by a factor of 1 over c, and if it's between 0 and 1, it's going to be stretched by a factor of 1 over c. And then inverse functions, f of negative 1x is really just a reflection of f of x across the line y equals x. So the first thing we're going to look at is our cosine functions. Our starting equation is 1/2 minus 1/2 cosine 2 of x minus pi over 3. So we're going to go through this and kind of break it down. We're going to start with just a regular cosine function. We have our period of 2 pi here. And then the first thing we're going to do is a phase shift. So I know it says minus pi over 3 there, but because we have this 2x right here, it messes with our shift, and we have to factor it out. So really, we're going to have a shift of minus pi over 6, which, we can see here with this line, kind of marking pi over 6, and that we've shifted to the right. And then after we shift, we still have a period of 2 pi. The period doesn't change, just where we start changes. We are going to have a horizontal shrink by 1/2. Basically the same thing as taking our 2 pi period and dividing it by 2, so pi. And after that, what we have is we have a vertical shrink because we have 1/2 in there. And so now our amplitude instead of 1 is going to be 1/2. And the next thing we have to do is reflect it over the x-axis because we have a negative on that vertical 1/2. And then all that's left after that is to shift it upwards by 1/2. So opposed to the original graph where we had an amplitude of 1 and it went from 1 to negative 1, we have an amplitude of 0.5 and it goes from 1 to 0. And instead of having a period of 2 pi, we have a period of pi, which we can see right down here with the amplitude of 0.5 and the period of pi. Moving on to our sine function, we have y equals 3 plus 2 sine 3x plus 1. And because we have parentheses here, we can see that the 3 is already factored out, so there's nothing we have to do there. So we're going to start with our sine function, just like last time. Period of 2 pi, amplitude of 1, nothing's really changed yet. But we do have a shift of 1, so we are going to move it 1 to the left. See right here, this, our shift where it's starting now. It doesn't change the period because it's still a 2 pi period, it just changes where we start. But this shrinkage by 3 is definitely going to change the period. So instead of it being 2 pi, it's now 2 pi over 3. And then the next thing we're going to do is we have a vertical stretch, because this 2 right here is, bigger than 1. So now it's going to affect our amplitude in a pretty big way. Instead of it being just 1, our amplitude is now going to be 2. Our period doesn't change. It's still 2 pi over 3, but now our amplitude does. And then our last thing we have to do is we have to shift it up by 3. So the graph looks like it's changed a lot. Instead of being from 1 to -1 like it was before, it's now 5 to 1 with an amplitude of 3, and instead of having that 2 pi period, it has a period of 2 pi over 3, which we can see right down here. So with tangent functions, it's going to be a little different. Tangent functions have a period of pi instead of 2 pi, and then they have asymptotes at the beginning and the end of the period. So it doesn't really have a clear amplitude because of those asymptotes. But nevertheless, we're going to start with our regular tangent function, which right here you can kind of see we have our pi period and, how it's working up to those asymptotes. And then the first thing we're going to do is a shift, but like our cosine function, this pi has to be factored out because we're not getting our true phase shift. So when we factor out pi, we realize we have to shift it by 1. So, we have our same period, but, shifting by 1 here. It's shifting to the right. And the next thing we have to do after that is we have to apply our horizontal shrink of pi. Same pi we factored out, just to get it away from the x and the 1. When we do this, though, our period is no longer pi. It's the same thing as saying, oh, well, pi over pi divided by pi is just 1. So now we have a period of 1. And then the last thing we have to do is a vertical shrink of 1/2. So again, it doesn't really affect the amplitude a whole bunch because there's not really a clear amplitude. It just kind of goes on forever. But our period does change, and our period goes from pi to 1. With our second tangent function, we have -2 tan 2x minus pi over 3. So right away we can see this is kind of the same situation we had before, where we're going to have to factor out that 2, but we can do that in a minute. We're going to start off with our tangent graph, and then the next thing we're going to do, here we have to factor out our 2, where pi over 3 turns into pi over 6, just like with our cosine graph. So we're going to move to the right by pi over 6, and then we got to bring this 2 back to do a horizontal shrinking. And here we're going to take our pi period and we're dividing that by 2 because of the shrink. So our period is going to be pi over 2. And then we have a negative right here next to the 2. So we have to reflect the graph over the x-axis because all of our y's are going to be negative. And then the next thing we do is a stretch by 2, which I know the stretches are hard to see because, the graph doesn't really have an amplitude and there's no really clear definition of where it stops. But that line does get a little less compressed, which is where we can kind of see our stretch. But we have a period now of pi over 2. So, getting into special right triangles, we have 2 types. The first type we're going to look at is a 30, 60, 90, which has the ratios of 1, square root 3, and 2. So we really want to visualize this triangle. We have our 30 degrees right here, our 60 degrees right here, and our 90 right here. When it comes to this side, this is going to be our 1. This side on here on the bottom is going to be our square root 3. And this sign up here, the hypotenuse, is going to be 2. And it's like this because if we take the sine of 30, we have 1/2. And if we take the sine of 60, we have square root 3 over 2. So our second right triangle is going to be 45, 45, 90. And this is going to have the ratio of 1, 1, 2. And when we look at this triangle, we have our 45 here, 45 here, And then we have 1, 1, and square root 2. And so you may be thinking, like, well, how do you get square root 2 over 2 if it's just 1 and square root 2 here? So if you take the sine of 45, it's 1 over square root 2. But because you can't have a square root in the denominator, it's going to turn into square root 2 over 2 because you have to multiply both the top and the bottom by square root of 2. And so, 1 times square root 2 is square root of 2. And on the bottom, that 2, the square root cancels out, and it's just 2. So, for special right triangles, we can use our ratios. So we know that our hypotenuse, which is 25, would usually be 2, and our x is on our one side. So it's just like, how do we take this and get 1? So because this would be 2, we just divide it by 2, and our x is 25 over 2. Or if you want to use decimals, I know I didn't put it in here, but it's 12.5. And then for this one, we have our hypotenuse, which is 2 again. We have our 60 degrees, letting us know it's a 30, 60, 90 triangle. And using those rules, we know that this side right here is going to be 1, and this side is going to be square root of 3. So how to get there is, because this is 2, we can't just multiply that straight away by square root of 3. We have to turn it into 1 first. So we have to divide it by 2, which gives us 6.5. And then once we have 6.5, now we can multiply it by square root of 3. And I use decimals here, so it's 6.5 square root 3, or it could be 13 square root 3 over 2. And then for our last 30, 60, 90 triangle over here, we have where 4 would equal 1. So we don't really have to change anything there, but we do need to find the side where our ratio is square root of 3. So we can just multiply 4 times square root of 3, and that's our answer. And then for D, we have our 45, 45, 90 triangle. And both of these sides, the 12, are our 1 sides. So, we don't really have to do anything there to get it to be 1. But for our x, we do have to find the square root of 2 side. So it's just going to be 12 times the square root of 2, which gives us x equals 12 square root of 2. So moving into the trigonometric identities and the quadrants, we have 3 main functions and equations that we look at when we talk about, solving these. So our first one is sine squared of x plus cosine squared of x equals 1. And using this function, we can get both of our other 2 functions. So when we look at tangent squared plus 1 squared equals secant squared, we may be thinking, oh, where do we get this from? Well, if we look back at our original equation of sine squared plus cosine squared, if we divide both sides by cosine, then we get sine squared over cosine squared plus cosine squared over cosine squared equals 1 over cosine squared. And if we simplify that, we know that sine over cosine is tangent, so if we have them both squared, it's just going to be tangent squared. The cosine and the cosine cancel themselves out, so now it's just 1. And 1 over cosine is secant, so we have secant squared. But if we want to take it the other way and divide both sides by sine instead of cosine, then we would have sine over sine squared plus cosine squared over sine squared equals 1 over sine squared. And the 2 sines would cancel themselves out, so we get 1. And the cosine would be divided by sine, so we would get cotangent. And then we would have 1 over sine squared, which is cosecant. So now looking on how to solve these, if we know that tangent equals 2 over 3, and the angle is in our third quadrant, we can find cosine by using tangent squared plus 1 equals secant squared. So if we look at this and we square it, because we need to get our tangent to equal tangent squared, we get 4 over 9. And when we plug that back in our equation, we get 4 over 9 plus 1 equals secant squared of x. And we can just combine 4 over 9 and 1 to get 13 over 9 equals secant squared. And from there, we need to find cosine. And we know that secant we know that secant is 1 over cosine, so what we can do is we can flip it and have 9 over 13 equals cosine squared. And since it's still squared right here, we have to square both sides to get the square root of 9 over 13 equals cosine of x. And because we have this information that it's in quadrant 3, we know that cosine is going to be negative, so it's negative square root 9 over 3. Or, not 3, 13. We know that it's negative square root 9 over 13 equals cosine of x. So for our last question, it's a pretty large, question. We have if secant equals 2 and theta is in quadrant 4, what are the other 5 trigonometric functions of theta? So, because we have secant equals 2, we can go ahead and start with our tangent squared plus 1 equals secant squared, which is the same one as last time. And we can see that if we square secant, we get 4. And adding that into our equation, we have tan squared plus 1 equals 4. So we subtract 1 from both sides and get tan squared equals 3. And then we square both sides of that, and we get tangent of x equals square root of 3. And we know that tangent is going to be negative because we're in quadrant 4, where cosine is positive and sine is negative. And so to get cotangent, super easy. Cotangent is just 1 over tangent. And so we have cotangent equals 1 over square root of 3. But because you can't have a square root in the denominator, it becomes square root 3 over 3. And because tangent is negative, cotangent is also going to be negative. The next thing we can use is we can use our cotangent to find cosecant. So we have 1 over cotangent. Oh my gosh. So we can use our cotangent to find our cosecant. If we square our cotangent, we get 3 over 9. And then we can plug that into our equation right here. 1 plus 3 over 9 equals cosecant. And so when we do this, we get 12 over 9 equals cosecant. And what we can do is we can break this 12 up into 4 times 3. That way it makes it a little bit easier when we square it, and we get 2 square root 3 over 3. And again, it's negative because sine is always going to be negative in quadrant 4. So cosecant is going to be negative also. When we look at cosecant, we can find sine, which is just cosecant is 1 over sine. And so if we flip it, we get sine of x equals square root 3 over 2. And it's obviously negative because sine is always going to be negative in quadrant 4. And then using sine, we can find cosine, which is our last one we have to find. And if we square that, we can get 3 over 4. So we can plug 3 over 4 into our equation here, and 3 over 4 plus cosine of x equals 1. And then you subtract the 3 over 4 from the 1, and we can get cosine squared equals 1 over 4. And then when we square root that, it's cosine equals 1/2. So when we look at our 5 functions together, we have sine of x equals negative square root 3 over 2. Cosine is 1/2. Cosecant is negative 2 square root 3 over 2, over 3, sorry. Cosecant is negative 2 square root 3 over 3. Tangent is negative square root 3. Cotangent is negative square root 3 over 3. So, now we're done. After going through this, you can effectively transform sine, cosine, and tangent graphs, follow the rules of special triangles to solve the sides for x, and know how to identify which trigonometric identity to use when solving, and how the quadrant affects the outcome. I hope you all have a good day. Goodbye.